very good. Hey, good afternoon. Hey, this is Bob Sullivan. I'm the CEO of PureLine, and we are starting our webinar series on Legionella control. Now, look, we put this together so that it kind of offers all sides of Legionella control. Today, I will be joined by Dr. Greg Simpson. He's written a number of books on, all types of disinfection strategies. And then very importantly, we're going to get, I picked a few panelists from our different customers. I've got Mr. Greg Bova. Greg works at Johns Hopkins and is intimately involved in Legionella control and always has a lot to add to a topic like this. So I'm going to be relying on him for some of the color commentation, if you don't mind. Now, again, this is the first of four. This meeting is only going to last 30 minutes plus any Q&A time after that. You can, at the Q&A period, you can either click on the little button below and submit a question, and we'll try to address that either during the presentation or just during the Q&A session. But let's go ahead and let me run you through a little bit of background. This first one is all kind of focused on PureLine, and we just want to talk about what we do, and then I want to get you into some of the science. When we get to that, I'm going to turn it over to Dr. Greg Simpson, and let's see what I can take you through here. All right, so the first one, who is PureLine? It's a privately held company, scientifically based, with actually going on 28 years now. All of our products are made right in the United States. And our focus really is chlorine dioxide. We do everything and anything with chlorine dioxide to eliminate harmful pathogens, bad odors, mold, mildew, right across the line. Because of this, we develop a lot of disinfection and preventative treatments. All of our products are EPA registered, and we operate in North America, Latin America, and the Middle East. So with that, let's talk just briefly about what is chlorine dioxide. The first thing I always have to tell everybody, and I know this sounds a little sophomoric in a sense, but chlorine dioxide, it is not chlorine. It does not operate like chlorine, and it really doesn't look like chlorine. Yes, it serves off the periodic table a Cl, which is your chlorine molecule. But what chlorine dioxide is not chlorine. And I'm going to try to take you more into that as we go further. So chlorine dioxide is a dissolved gas. What does that mean? Even in the liquid phase, when you put it into water, such as your hospital water, healthcare water, it is still a gas and will always try to release itself from there. It is probably the most effective in destroying a biofilm. Now, that's important when you think about a dissolved gas, because the gas is so small, it is able to kind of penetrate the biofilm. Biofilms, if you read some of the studies and just some of the physiology of them, the gas is able to get inside of the whole layers of biofilm, get towards the back of it, and basically destroy it. So EPA has approved chlorine dioxide as a sterilant since 1988. It's been approved by water treatment, by the FDA, USDA, food industry. We use it in all types of markets, poultry, vegetable wash. Unbeknownst to many people, it's one of the few chemicals you can use on organic vegetables and still call it organic. And I have a lot of people think, well, that's a big surprise. I thought my organic vegetables didn't have any chemicals on them. Well, that's a great idea if you're going to the farmer's market, but when you're talking about commercially available organic product, it really does have to have some type of treatment. And chlorine dioxide, because it leaves no residue, is the perfect candidate. It is a sterilant. It is capable of the 6 log reduction, which is represented by the 99.9999%. It's safe to use on once-through applications. Now, what does that mean? In some hospitals or in some industrial applications, they actually have to treat the water with chlorine dioxide, and then they send it through the system, whatever they're doing with it, and then let it go to drain. So for example, in a hospital, maybe you're letting some of your water go to drain for whatever reasons. And some of it goes to drain just because it's going through the shower. But in a once-through application, it basically comes in, goes out, and the chlorine dioxide is managed to a level where it will have no impact on either your water treatment facility, or in some cases, in some of our industrial applications, they actually then put the water back into a river. It's a strong oxidizing biocide that kills microorganisms. It disrupts the nutrients across the cell rather than disrupting the metabolic process. Here's an easier way of saying it. Chlorine destroys from the outside. Chlorine, in a sense, is a poison. Chlorine dioxide is going to destroy the cell from within. For that reason, if you look at the last bullet, bacteria cannot develop a resistance to chlorine dioxide. Very, very important. If you guys have ever been in a situation in your healthcare facilities and that you used, whether it be copper, silver, or something else, you end up with a situation where the product creates a resistance. Sorry, guys, I'm trying to shut up the phone at the same time, and I did. Sorry. Anyway, so it develops a resistance to it, and then that does nothing but then drive any of the facilities people absolutely crazy. So where is it used? Guys, we use this in so many different industries: pulp and paper, municipal and drinking water, food processing industry. We already talked about the organic vegetables, the healthcare industries, and I could go on and on. We're in the poultry business. We are in desalination. We are in the fumigation business with the same product for the Kraft and Kellogg's of the world. So it's a sterilant. Now, there's a sterilant, there's a disinfectant, and there's a sanitizer. The sterilant has responsibility for a 6-log reduction, which is where chlorine dioxide is most effective and most desired. It's a disinfectant. It means it eliminates most contaminants, and if it sanitizes, it reduces the risk. So chlorine dioxide is at the top of the food chain in terms of removing contaminants. Let's go ahead and look at some of the technologies that are out here right now that many of you are either employing or you have been thinking about. Now, remember, this is only our first webinar. In a couple of weeks, we go through the second webinar. In that webinar, we're going to get into some of the strategies for using these and selecting them. So this is very, very top level at this point. There's chlorine. It's an approved, EPA approved. Most of it comes sometimes in your water. Sometimes people then will add more chlorine. You have monochloramines. You have chlorine dioxide. You have copper, silver. You have UV radiation, and then you have ozone. Right. So those are the basic technologies. What I'm going to do is have Greg Simpson kind of take over here. And Dr. Greg has written a number of books. Check his books out on Amazon. Greg, you've been with PureLine what, for 7 years?
Probably about that.
Okay, well, right in there. Greg, why don't you take it through from here, and let's just run through some of the things they need to understand about Legionella and some of these technologies.
Okay, I apologize if I'm going to repeat ground that's already been plowed in terms of Legionella. Most people that work in hospitals already have a good handle on Legionella or have a plan in place. Legionella was discovered in the late 70s, and it resulted from an outbreak of people who got sick at an American Legion convention. Those are mostly older people, had compromised immune systems, and 221 people got sick and 34 died. And then the researchers finally found and identified the bacterium that was responsible, and they named it Legionella phaenophila for obvious reasons. And because it gave a person pneumonia and they died or they got real sick. The disease which causes death is called Legionnaire's disease, and there's a non-fatal illness called Pontiac fever. There's a specific serotype that's involved, and I don't want to get into the weeds on all that stuff. Next slide. Legionella are ubiquitous in the environment. They are everywhere. The question is, why don't people get sick all the time? Well, Legionella mostly grow in protected micro niches, such as in biofilm and algae inside protozoa. So any control strategy must include control of biofilm, algae, and protozoa. Of course, if you got protozoa in your system, disinfection has been really poor, because that's a higher life form that doesn't normally survive disinfection anyway. Next slide. Legionella have been found to be the reason that they don't cause more problems than they do is because they are the 90-pound weakling of bulk water bacteria. That is, they don't produce an antibiotic that would allow them to compete effectively for nutrient. They're competed for by every bacteria pretty much out there. And so they don't grow in the bulk water very well at all. They have to hide in places like biofilm predominantly, and other places. So they got to grow in the biofilm in places like that. Okay, next slide. This shows, for biofilm control, this shows relative effectiveness of biocide on Legionella, and well, on just biofilm. Just doesn't talk about Legionella. Chlorine is relatively ineffective. I had a conversation one time with a guy named Bill Costerton, who was at the time the director of the Center of Biofilm Engineering at Montana State, which is kind of the premier place for doing biofilm testing. It's a multidisciplinary department that gets involved with physicists and engineers and microbiologists and all kinds of different technologies. And one of the things they have done is they have done a lot of testing with chlorine, and it's not very effective on biofilm. So the logical question is, if it's not very effective on biofilm, why is it used? And the reason is it can kind of suppress the biofilm in dilute nutrient solutions. But if there's a lot of bug food present, chlorine loses out. The biofilm can overpower the chlorine. We've treated a number of cooling systems where there were process leaks that caused the biofilm to grow so fast that using chlorine, they just couldn't keep up. Ozone generally doesn't, is not very effective on algae. I was talking about Bill Costerton. He told me that the stronger the oxidant, in terms of oxidation potential, I guess, the stronger the oxidant, the less it penetrates biofilm. So chlorine and ozone being very strong oxidants do not penetrate biofilm. Chloramines are able to penetrate the biofilm, but they don't remove it. Chlorine dioxide occupies a kind of a narrow place where it's not only it penetrates effectively, but it also removes the biofilm. And I can say that pretty positively for reasons I'll talk about in a minute. And then there's some other non-oxidizing biocides that aren't very effective on biofilm. Generally, non-oxidizing biocides, I mean, are not very effective on biofilm. Okay, next slide, please.
Hey, Greg, hey, Greg Bova, can you give us kind of a Johns Hopkins practical, perspective on biofilms and the impact and kind of how you see biofilms and what you try to control?
Yeah, hi everybody. So about 20 years ago, believe it or not, I looked at different disinfection methods, the chlorine, monochloramines, copper, silver, and all that. And a big concern was the biofilm. And so just as Greg Simpson stated that, the chlorine, ozone, and chloramines, they really don't penetrate the biofilm. And so the attacking from outside in, what happens is that the biofilm develops a protective layer. So you may suppress it, but don't eliminate it. And so, but everything I read about the chlorine dioxide, because of its penetration abilities, that it kills from within, it can strip the biofilm. So, over 20 years ago, that's why we went down that route.
Great, thank you. Greg, I'll give you next slide.
Okay, so we've talked about the penetrating ability of chlorine dioxide. The reason it penetrates, as Greg said, is that it's uncharged and it's relatively nonpolar. For example, this picture on the right shows a layer of 3,000 parts per million chlorine dioxide. And I carefully poured a layer of normal hexane on top of it. within just seconds, the hexane layer was every bit as yellow colored as the water. The chlorine dioxide did not even see that organic barrier, that water organic barrier. It just went right into the nonpolar hexane. And we think that is one of the reasons why it is so effective on biofilm. This happens in cellular walls. Chlorine dioxide goes right through the cellular wall and inactivates, my pet theory is it inactivates some sulfhydryl group on some enzyme, some key enzyme in there, and kills the bacteria. And research has shown chlorine dioxide is actually 4 times more soluble in cyclohexane than it is in water. So this is an important point. If you had a layer of water that had 3,000 parts per million of chlorine in it, and you poured hexane on the top, you could wait for a year and it would still remain white because the chlorine will not penetrate that organic layer. It's polar and it's charged. So,
and Greg, I think that's why we see some of our industrial customers actually use chlorine dioxide as a disinfectant before an RO filter, because they want to keep the surface of the RO filter clean, and the chlorine dioxide has the ability to penetrate an RO filter.
right. We did a field trial at Tampa Bay Water 20 years ago or more. And everybody always wants to say, well, we're afraid you'll tear our RO membranes up, and so let's use used RO membranes. Well, I wouldn't let them do it, because I said the problem is you've already got bacteria having lunch on that RO membrane, and if you put chlorine dioxide in there, it's going to strip off that bacteria and the biofilm associated with it, and you're going to get salt leakage. And people say, well, see, chlorine dioxide chewed a hole in our membrane, but that's not what happened at all. And that's exactly what we got them to use new RO membranes, and it basically verified what we were saying.
Yeah, I've got 1,000 stories of people saying, well, we destroyed all the things on the wall of the pipe, but we found out we didn't have a pipe.
Yeah.
All right, here you go. Here's your next slide.
Okay. This is some work that was done at Montana State at the Center of Biofilm Engineering. We've said chlorine is not very good for biofilm removal, and chlorine dioxide is. This is, you'll have to, okay. This is an application of 50 parts per million of chlorine over an hour period of time, and it just kind of takes off the surface and doesn't really penetrate very well. The next slide shows what happens with chlorine dioxide. 10 parts per million of chlorine dioxide for 60 minutes basically just removes the biofilm. And we've been saying that all along because we could see it open exchangers and petrochemical plants and things, but we never had any documentation until we got this from the Center of Biofilm Engineering. So next slide, please. Algae protect Legionella. Certain algae are known to provide nutrients that Legionella needs. In a 1980 survey of places all over the place, aquatic habitats, Legionella was found to be present in all the algal mats. The results suggested Legionella was using metabolites produced by algae as a nutrient. Chlorine dioxide is superior to all other oxidants for controlling algae. The first use of chlorine dioxide in the US was to control algae at Niagara Falls. That second paper down there by Dr. Sinan discusses that first application in Niagara Falls. Next slide, please.
All right, and guys, I do want to remind you, you're getting the 10,000-foot view from PureLine. The next 3 webinars will also discuss all the other technology, and you'll see some of it here. But I don't want you to think that this is a 4 series of talking about chlorine dioxide. But let's see where we go from here.
Okay, one of the other mechanisms for the survival and protection of Legionella is that protozoa, some protozoa, you know, you think of them like microscopic cows, at least as a non-microbiologist, I can think of them that way. And these microscopic cows are grazing on the biofilm, and they eat the bacteria. And I think eat's the wrong term, but that's how I tend to think of it. And so normally when an amoeba engulfs a bacterium, basically the bacterium dissolves inside. But the Legionella had the ability to put out some kind of protective chemical that basically shuts the amoeba's ability to digest them down. And these Legionella find themselves in a protected environment, and they begin to multiply like crazy. And you can see 2, 3, and 4 as these vesicles, they're called, grow, and they're packed with Legionella. And number 5 there shows an actual a photo of an amplification inside an amoeba. And once an amoeba senses that it has been invaded by these Legionella, it begins the process of encysting, that is, going dormant. And if it wins, then it goes dormant, but the Legionella are still there and they stay there for a long time. If it doesn't, if it loses, then the pressure inside builds up and the amoeba blows up and releases these zillions of little Legionella into the environment. And the interesting thing is that research shows that those Legionella that have been released are physiologically different from the ones that are just found in the water normally. They are motile, they move around, they're more virulent. I call them ninja Legionella.
Yeah, too many grandkids.
Yeah. Once an amoeba gets infected with the Legionella, you can kill them with various oxidants, and generally the pecking order is that ozone's better than chlorine dioxide, which is better than chlorine, which is much better than monochloramine. But one research paper showed that an encysted protozoa, an acanthamoeba that had been full of Legionella, was very resistant to up to 50 parts per million of chlorine. Now, the table below shows a different organism, and the purpose of this table is to kind of show the difference in order of magnitude of oxidant it takes to kill something that's very resistant. This is a Cryptosporidium parvum oocyst, and it's not a cyst, but it's kind of like a cyst. The only reason I'm showing this is because the range of concentrations required, the CT values required to kill it. This was done by Korich and other coworkers, and when we were doing a trial run yesterday, the question was brought up about EPA, and so it looks like because even ozone is so bad at killing this particular organism, drinking water facilities rely on filtration as the primary means of removal in potable water, and you only have to get 2 logs. Greg, Bova, you got any comments about that?
Yeah, well, to add to this, the importance about understanding the reaction times is critical, because being in a hospital, the water comes in, and within 15 minutes, that water that's coming in is being utilized. So you don't have the luxury of, having extended contact time to kill the organisms. And so the chlorine dioxide has a rapid effect against the organisms, and it has a residual effect, where ozone, it's great, but it has no residual effect downstream. So if you have biofilm in a pipe, it's not going to do anything for you. But that's the key reasons for looking for a very reactive but low dose level of disinfectant, because the EPA regulates the limits. So if you look at monochloramines and chlorine, it's 4 parts per million. So, you're not going to kill what's coming
Okay. Greg, next slide.
Yes, sir. That may be it. I don't think so.
I don't think so. I'm stuck. Try that.
Oh, okay. We included copper silver primarily because it's used for Legionella in some cases. the way this thing works is copper and silver are pretty far away from each other in the galvanic table, and so they release ions of copper and silver, and those are both known to be pretty antibacterial, have antibacterial properties. It's been used in a number of hospitals to treat against Legionella. There are a number of drawbacks, though. Controlling the residual can be very difficult because it's very flow related, and flows in hospitals are somewhat difficult to control. There's a lot of flow during the day, and the flow basically stops at night. Legionella can also develop a resistance to this technology, and that's thought to maybe be flow related. It loses effectiveness over time. And I had a friend who was a consultant, or I have a friend who is a consultant, and he and I had a discussion one time about, he had 2 hospitals he was doing investigative work on, trying to analyze why the galvanic pipe in the hospital went away. And he basically showed that it was galvanic corrosion, because galvanized steel is real far away from the copper and silver. So that's next slide.
Okay. And so, and guys, these are these look at the next 3 webinars. And so you can see we're in the second one, we're going to talk about selecting the best water disinfection method for your facility. And keep in mind, everybody's a little bit different, which is why we have Greg Bova on here, and we're going to have some others who are going to be able to give some kind of color commentation in terms of what they use and what they choose. The third presentation, carbon filtration and water disinfection system, and the whole installation process. And then I think this all builds up to, and how we got connected to Greg Bova. So Greg, we've sold equipment, to Johns Hopkins for a decade or so. But he gave a presentation at a meeting, and I'll tell you what, it was worth its salt. And that's really what's in the 4th meeting. Now also, and as we've told you in the webinar series, at the end of this, we're gonna have a little drawing, and we're gonna give away a $100,000 HP chlorine dioxide generator. Okay, so with that, let's go ahead and go to the Q&A. And if we can, Alex, how do I open that up?
Yeah, so if you go ahead and hit that Q&A tab, you should be able to see one of the questions. And I think Suzanne had a question for the team that I think Greg responded via text, but I think it would be appropriate for you to discuss over voice for everybody.
Greg, did you respond to it?
I did. She was asking about whether we had products that would do a hospital remediation that would contaminate Legionella. The big problem in hospitals is dead legs. You've got to, when the way they are engineering hospitals, or the way they used to, is they would have a big line of pipe in the wall, and they would have an extension in case they ever wanted to expand. Well, I don't know if they quit doing that or not, but that made it very difficult to do remediations in hospitals. We did that with Pure 3000 on several occasions. So
Greg, explain to them, Pure 3000, guys, is just our liquid chlorine dioxide product. If you don't want to buy a generator, it's just chlorine dioxide in a drum.
So can I add to that that question? So years ago, that the hospital recognized this problem, and so all piping now that's designed is properly sized, as well as we eliminate dead legs. And everywhere we had a dead leg, we took it out, and that was because of this issue of not being able to remediate and to do normal flushing. One of the issues that we contend with is not dead legs, but inactive legs. You could have a pipe that's sized for like 10 showers, but maybe only 1 shower is being utilized. Yeah. So that was a challenge for us that we overcame years ago. But I just want to add on to that.
Yeah, there's a lot, guys, this goes way beyond healthcare on these dead legs. we have a lot of industrial customers who fight this all the time. And it's just so important to design, if you get this opportunity, and the food industry calls it hygienic design, but design to make sure that there are no dead legs and that your facilities people know that you don't contract in dead legs. Well, we're going to cut it off here. You actually repair that pipe, kind of from start to finish. On another note here is recently in the news was a woman out of Indianapolis. They went away to Florida for the winter, came back and drank some of the water from her faucet, ended up with a severe form of Legionnaire's disease, and amputations and all other things that had happened to her in a short period of time, just from drinking water that had not been used. So Greg Bova's comment about not just dead legs, but also legs that are seldom used or not used very much at all.
Hey, Bob, I like to let everybody know also something very important that we picked up years ago, that the EPA related to public water use is the disinfection of that water is geared towards the general public, which is considered healthy. A hospital deals with people that are sick. And so your immune systems could be compromised and therefore making you more susceptible towards these waterborne pathogens that normally, if you're healthy, it's not going to bother you. So, we had to look at, to destroy these pathogenic organisms that could be detrimental to our patients and not for the general public.
Great comment. Alex, I can't seem to open the Q&A. Can you provide the questions?
I think Suzanne was commenting again that they've had troubles with dead legs for some areas of the hospital, but that it's been shut down for months. So it seems like, this is quite relevant.
Yeah, well, very good. All right, so at this point, ladies and gentlemen, we're going to conclude unless there's any other questions. And again, I would encourage you to come back. I mean, the big payoff is the fourth one, but you're going to get some of the nuts and bolts from some people that have been in the bellies of these hospitals and can probably provide some very good comments that I think will help you understand different strategies for Legionella control and what will really fit your hospital. So with that, I will depart with no other questions. Thank you very much.